This lesson will be about making proportions within a triangle. There in your cipher, go ahead and make yourself an acute scalene triangle, a few inches wide. You need to be able to mark on it a little bit. So an acute scalene triangle. And after you do that, pick one of the sides, any of the sides, it doesn't matter. Draw a line parallel, slicing through it. Go ahead and mark it as parallel. Then draw you another one. Probably a different distance, doesn't have to be. Maybe you can do a little bit better on your parallel than I did. Okay, notice we've got at least two triangles here. I'll mark the big one so I can refer to them and distinguish which ones I'm talking about. So there's the big one, and I'll mark this smaller one on the interior. So I've got a pink triangle and a blue triangle. Are they similar? Indeed they are. Let's investigate that. Of course, this angle here is common, so it's the same in both triangles. So we have one angle that's the same. We just need one more under angle, angle to ensure that the triangles are similar. We'll have parallel lines. Parallel lines with a transversal. Transversal. Corresponding angles, the blue angle here, the pink angle here are corresponding and they are congruent. Therefore, we have two angles. By the way, there's also a transversal here, and these are also corresponding angles. So we have an abundance of angles that are congruent. We have all three. We actually have angle, 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 which we didn't need. All we need is angle, angle. So they're congruent. Okay, let's look at this a minute and see what it gets us. It gets us, well, the pink side to the blue side on the top is proportional to the pink side on the bottom and the blue side on the bottom. So pink top is to blue top as pink bottom is to blue bottom. Corresponding sides are proportionate. Makes a proportion. Well, what does that tell us about the leftover piece here? I've got that in the triangle. But what about this leftover green piece? Does it have any relationship? Well, look how it works. As this side comes in, again at the same rate, it slices the green and then down to the blue at the same rate because the lines are still parallel. So as the top green decreases, the bottom green also decreases. Since it's not isosceles, it's not at exactly the same rate, but the rate is steady as it goes. So as the top it decreases, the bottom decreases, and their rates remain constant, so the line remains parallel. Oh, wait, it's the same rate, so they are in the same proportion. So from here to here to here, these pieces are going to remain in the same proportion. So we'll have this is to this, as this is to this, top green piece, bottom green piece, top green piece, bottom green piece. And the blue piece is, and the yellow piece is the same. And then also to here, because each one of these are triangles, and they're that leftover part of the triangle that is being decreased at the same rate. Since the rate stays the same, it remains proportional. So what that'll look like when I do a whole bunch of them, is this. So now by analogy, by extension to the same argument that I just made, you should be able to see, I hope, that A is to B, as C is to D, as E is to F, as G is to H, as I is to J. Because in each event, we're sliding and closing up the triangle to make a smaller triangle each time, and the two triangles will have the side at the same angle, and every time we do it, the rate will remain the same, so these will remain in proportion. That gives us the triangle proportionality theorem. We demonstrated it, we didn't prove it. We can also write, okay, so what we have here as given in the theorem straight on, we have that AD is to D, is to AE, no, I'm sorry, AD is to DB as AE is to EC. So we have piece is to piece on the same side as piece is to piece on the other side. So that's one way to do it. AD is to DB as AE is to EC. Notice that we can switch the means and have a way to arrange it that might also be helpful from time to time. So I've switched the means here. So now I can say AD is to AE as DB is to CE. So top piece, bottom piece, top piece, bottom piece. Either way is acceptable. The straight-on theorem has it on the individual sides, and switching the means gives us top pieces to bottom piece, top pieces to bottom piece to give us that proportion. Okay. And there's a converse. If it's parallel, then it divides it proportionally, and here's the converse. If it's proportional, then it's parallel. So this is a way to get the parallel. So just as when we were doing other things with parallel lines, notice that the straight on starts with it parallel and goes to proportion in this case, and the converse starts with proportion and goes back to parallel. So the original and the converse go in the same direction. So let's look back at this triangle. We're going to do a little magic on this triangle. No triangle is harmed in the making of this. Okay, let's imagine. Okay, we've got A is to B, is C is to D, is E is to F, is E is to, right? Okay, so we know that those work. But what happens if I just cover up this end, cover up this end? It's still true. C is to D, as E is to F, as G is to H. All the ones that are between the parallel lines are still proportional. But notice the ones on the end we're not sure about anymore, because we don't know how far that's going to go. Right there, it's not parallel. We don't have the same little magic with the triangles that we worked before. Over here it's the same. There's no point down there. We don't have the same little magic to make them proportionate. We don't. So, because we don't have the same angle there, so we don't have similar triangles. Okay, so it's not going to work. But notice that doesn't mean that the ones that are between still don't work. Thus we have, and I just kind of made up this name, but it's just kind of an abbreviation, but you're allowed to use it because it kind of looks like slicing. Kind of like slicing through. Now, something that might help you remember it. Let's say we've got a loaf of bread that was made kind of funny looking, Yeah, it's too funny looking. How about kind of like this? Something like that. And then we've got some slices going through it. I'll make them green. This is like you go down to the Kroger's where they let you slice your own bread, and you slice your bread. So this is a piece of bread that's shaped kind of funny. Notice that where the proportions are the crust between the knife blades. So these are the knife blades going through cutting the bread at the bread slicing machine at Kroger's. Makes them nice and parallel. Where the proportions are between the parallel cuts, between the knife blades. The heel of the bread, the end of the bread, and the other end of the bread are not included in that. Because once you get out here, you don't know what's happening. Once you get out here, you know what's happening. So you got a piece of bread, you're getting it sliced, you run it through the slicing machine. The crusts of the slices, not the heels, the crust of the slices are parallel. The slicing is parallel, the crusts are proportional, and the heels don't work. They're nothing. So you might as well forget them. And notice that the crust is where the proportional things are, not on the heel. Okay. Angle bisectors. I'm going to say that this is an angle bisector. The red bisects the angle, the purple, blue angle. So I'll mark it here. These two are congruent. The red is an angle bisector. Look at it. It doesn't do much other than bisect it. It's not like a median. It doesn't go to the midpoint. So the yellow side is not equal. The purple and blue side are not equal. The only thing that's equal is the angle that's bisected and the red side that's in common. The two triangles that are formed are not necessarily similar. They're not necessarily congruent. They're not necessarily anything. So we can't rely on what they are or what they are not. Notice again what happens as we slice. As we move it, excuse me, not slice. As we move it at the same rate, look at how the yellow portion on the top triangle gets smaller and the purple portion on the top triangle gets smaller. They still form congruent triangle, they form similar triangles here because the rate is changing the same. Look at the bottom. The rate's doing the same thing at the bottom. The yellow in the bottom triangle is getting smaller as the blue is getting smaller to make the smaller triangle. The rate stays the same as it changes. Since the rate stays the same, we can make ratios here. It's one rate made by the yellow side, the side that's opposite the bisected angle. So what we see there is that the piece of the opposite is to the side adjacent, as the other piece of the opposite is to the other adjacent side, the ones that's here at the angle that's bisected. So piece of the opposite is to the adjacent, as piece of the opposite is to the other adjacent. Okay. This is triangle proportionality. Oh, I'm sorry. This is the angle bisector. This one doesn't have a name. I'm sorry, I said the wrong thing. This is not triangle proportionality. This is the angle bisector makes proportions. I said the wrong thing. The angle bisector makes proportions. So the bisector here is still the red one. The piece of the one opposite is to the top, the one that's adjacent, as the other piece of the one opposite is to the bottom, the one that's adjacent. The way that it's stated here is the piece of the bisected one is to the other piece of the bisected one as the adjacent is to the other adjacent. Piece is to piece as top is to bottom. Notice we can switch the means again and write it in the other fashion. Either one is just fine. So the theorem is written is piece of the opposite is to the other piece as the top is to the bottom. Or piece is to piece as adjacent is to other adjacent. Piece is to other piece as adjacent is to other adjacent. When we switch the means, we get piece is to top as piece is to bottom. Piece is to top as other piece is to other side, the bottom. Piece is to top as piece is to bottom. Okay? So that's the angle bisector makes proportions. This is a no-name theorem, and you're welcome to use this as an abbreviation. It just kind of shortens that and helps you remember what it means. Okay, let's look at a few of these and how they work. Here we've got, well, let's look at this one. How are you going to find the length of AB? The lines are parallel, therefore they're sliced, like in the bread machine, proportionally. So we can say 3 is to 4 as AB is to 12, or we can say 3 is to AB as 4 is to 12. Those are not the same ratio, but they make the same proportion. They make a corresponding proportion, and it works just fine. So again, we got this one. Is it parallel? 18 is to 24 as 10 is to 15. Well, 18 and a half more is 24. 10 and a half more is 15, so it's the same rate. It's times 1.5 or times 3 over 2 will get us to it. So yes, these are parallel. Then the angles. Here the angle is bisected. You can say the piece of the opposite is to the side as the piece of the opposite is to the other side. Piece is to side as piece is to other side. Piece is to its adjacent side as the piece is to its adjacent side. X is to 14 as 15 is to 21. So you can solve that. This is the relationship 5 to 7. Putting it here, what would it be? 2. Okay. Another one. Okay, this one's going to get into ones that kids have troubles with, because we're asked what the N is. Remember with the bread, talked about the bread, you can't trust the heel, right? So we've got the bread cut into slices, parallel slices by the bread slicing machine. Everything that's between the blades that cut the bread forms a proportion at the crust, but the heels do not do the same thing. They are not in the same relationship. So what we've got here then is, for all of the ones that are on the crust portion, the portion that is the transversal, that's sliced by the parallel lines, those will make proportions. 12.5 is to B, as E is to 5, as 12 is to 15, as F is to 10. Those are not a problem. But the ends are no good. So if you need to find out the end, we do not have a shortcut for it. Since there's no shortcut for it, you have to go back to similar triangles. So you'll have to use the whole big triangle. This is to find A, the end, the heel, the whole big triangle, and then find one of these triangles that you know the piece, corresponding piece that you want. Here you want the left side, so this is going to be the left side. So big triangle, and then try this smaller triangle. So that'll be A is to 12.5, as all of these added up are to 15 plus 10. So A is to 20 plus B as 12.5 is to 25. Oh, 30, I'm sorry. A is to, I added it wrong, 30, I'm sorry. A is to B plus 30, sorry. A is to B plus 30 as 12.5 is to 25. That'll give you proportion based on complete triangles. The slicing exceptions are handy ways to do it. Only count for the outside portion of the bread and not for the heel. Okay. Here ends this lesson.